created every now and then. Thus, it can be said that condensed matter physics is one of the main pillars of high technology. In this highly active area, ICC 2023 intends to cover a few selected topics to be presented by well-known experts of this field. Besides this, ICC 2023 has provided an international platform to encourage young researchers to participate, present their recent research work, and interact with other participants. During the coming 2 days, we shall be awarding the deserving participants with Best Poster Awards, Best Oral Presentations, and Young Achievers Award. I hope this international conference will prove to be very fruitful for all of us and definitely achieve its goal. Thank you so much.
Thank you, Dr. Shivangi, for providing us with a comprehensive overview of the exciting programs that we have in store. Moving ahead, now I kindly request our guest of honor, Professor Sampath Vadera from IIT Jodhpur, to share his words of wisdom with all of us. I request you, sir.
Good morning and namaskar. Dignitaries on the dais, faculty members, delegates, and students. First of all, congratulations to Engineering College Bikaner for this wonderful event. Materials are something which are omnipresent, and condensed matter physics is another way of looking at material science. And I'm sure that this conference will bring people together, new ideas, new thoughts, and those kinds of things. When I was looking at, because I have been working in materials for about 40 years and so, they are present everywhere. Whatever you look at, they are present. Look at display, look at watch, look at whatever things around, they are everywhere. But what is current requirement? What are the problems? One of the major challenges today is that when you are doing new research, how sustainable it is and what way we are looking at it. So some of the challenges which we are facing now, they may be materials for energy, they may be kind of materials or research on maybe water technologies, maybe research on, I would say, quantum materials, which are emerging materials. So we can look at many kinds of things. Another area which perhaps we may look at is today computational materials or condensed matter physics. That's another area which we may look at. Of course, I will not take much time because we are already late and I'm supposed to speak after this session. So I wish all the best, and I'm sure that this conference will bring people together, new ideas, new thoughts, and I'm always happy to come to Bikaner. I have been coming to Bikaner quite often. My friend Ravindra Mangal is there, and whenever he sends me instructions that I have to come to Bikaner, I do come. So it is as per his instructions I am here. Thank you, Jai Hind, and looking forward to interacting with the people. Thank you.
Thank you so much, Professor Vadera. We are truly honored to have you with us today, and your speech has left us with indelible mark on this gathering today. Now I request Professor J.V. Yakmi, ex-Associate Director, Bharth Mumbai, to share his word of expertise and wisdom with us. Please.
Good morning, all of you, my young students, young friends, my not so young friends, and I am the only old person standing here. I want to say that I have been associated with the ICC from the beginning. My friend Manoj is there somewhere. Yeah. So I enjoyed all the times. Only one I missed, but this is the third time I am coming. And I want to say only one or two sentences. Number one, the people who are already well versed in research who are attending, they come to either exchange ideas or to tell each other what they have done, or maybe try to generate some opportunities for collaboration. But I am talking of the young people who are about to finish their PhD, or they have just finished PhD but they are looking for jobs, or there are some who think why they can't also become as good scientists, as good professors, as good academics. So I am more focusing on younger people. Even in my talk I will speak in general terms how to do well in science. So my young friends, you are the ones who will benefit maximum in such a conference by learning how a poster is presented, how a talk is presented, and how can people like Professor Badera impress people so much. So keep watching, keep learning, keep looking at very intently what is happening. Thank you.
Thank you, Professor Yaki. We carry with us the inspiration and insights you've provided us. Your presence has definitely enriched our event. Now I request Dr. Michelle D. Loro from IIT Italy to give away a few words of wisdom with us.
So, good morning, everyone, dear friends. First of all, I don't know if I'm, let's say, appropriate person for wisdom. Okay, so I apologize in advance. I just want to express how lucky I feel in being here on the other side of the world, looking from my perspective, to do what is my preferred activity, which is share idea of science and learn what other people are doing and try to convey what we are doing on the other side of the world. So it's even more lucky, I feel, because after the COVID experience, all the conferences were held via web. And now, I mean, having the possibility of traveling 12 hours to actually meet people, it's fantastic. And it's what gives, at least for me, the spirit to keep working in research. So I thank all the organizing committee and all of you attendees for, let's say, being with us in these 2 days of discovery and sharing, and I will certainly do my best. And I think that if everybody keeps doing his best in sharing ideas, research will be the key to a better future that we can work together for. Okay, thank you all.
Thank you so much, Dr. Loro. Your dedication to the field of physics and your generosity in sharing your knowledge are truly admirable. We are immensely grateful, sir. Ladies and gentlemen, now I request Professor Ravindra Mangal, President CMRS Society, to kindly convey a few words regarding the conference and formally welcome our guests and the participants for this conference. I request you, sir.
Thank you, madam. Namaste, सुप्रभात, very good morning to all of you. आप सब लोग बड़ी बड़ी दूर से लंबी लंबी जर्नी करके के बीकानेर पधारे हैं, तो मैं कंडेंस्ड मैटर रिसर्च सोसाइटी की तरफ से आप सभी का तहे दिल से, मन के अंदर से आपका सबका बहुत स्वागत करता हूं और आशा करता हूं कि आपका 2 दिन का जो यहाँ स्टे होगा वो न केवल साइंटिफिक वर्ल्ड को बल्कि हम सबको आपसे और सबको सीखने का बहुत मौका मिलेगा। बीकानेर की धरा मैं बेसिकली कहूँ कि सांख्य दर्शन, जो नंबर सिस्टम के बारे में, जो सांख्य दर्शन के बारे में जो बात की जाती है, उसके जो प्रणेता थे कपिल मुनि, उनकी धरा है। कोलायत यहाँ से 40 किलोमीटर दूर एक जगह है, वहाँ पे कपिल मुनि ने अपना जो सांख्य दर्शन के ऊपर जो पूरा काम करा है और उन्होंने विमानिकी के बारे में भी जो आइडिया दिए हैं, वो उसकी धरा है ये। बीकानेर को छोटी काशी कहा जाता है। छोटी काशी का मतलब काशी के बाद में स्मॉल काइंड है। यहाँ पे शहर के अंदर आप जाएंगे तो आपको हर तीसरा चौथा मकान के बाद में एक मंदिर मिलेगा और मंदिर को लोग जीते हैं। ये जो जगह है ये केवल सिंपल सी वैसी नहीं है, मन से लोग जुड़े हुए हैं, यहाँ पे बहुत जुड़े हुए हैं। तो ऐसी धरा जहाँ पे एक और कपिल मुनि है, दूसरी ओर करणी माता विराजमान है, तीसरी ओर अगर आप देखें तो पुनरासर बालाजी हैं और सालासर बालाजी, बहुत फेमस जो जगह हैं। तो बीकानेर इन सब से घिरा हुआ है। तो ये छोटी काशी जो नाम दिया हुआ है वो ऐसे ही नहीं दिया हुआ है, लोग इसको जीवन में जीते हैं और बहुत अच्छा करते हैं। इस धरा पे मैं आप सभी का स्वागत करता हूं और आशा करता हूं कि जो 2 दिन का डेलिब्रेशन होगा या कन्वर्सेशन होगा वो सभी सोसाइटी के लिए बहुत फ्रूटफुल रहेगा। मैं भी कॉलेज एजुकेशन से 84 से जुड़ा हुआ हूं और मेरे जो गुरु हैं वो संपत वडेरा ही हैं। ये हमारे रिसर्च कर रहे थे जब मैं एमएससी कर रहा था और इनसे मैंने बहुत सीखा कि किस तरीके से पढ़ाई करनी चाहिए। ये आप सभी जो न्यू रिसर्चर हैं उनके लिए एक बहुत बड़ा पॉइंट है। मैं आपको बताता हूं कि एक सीनियर जूनियर को किस तरीके से तैयार कर सकता है। ये जब हम आप पीएचडी कर रहे थे और मैं एमएससी कर रहा था और एक्सरे लैब मेरा स्पेशल सब्जेक्ट था, वहां पे ये क्या करते थे कि एक्सरे का एक्सपोजर कहते थे कि मंगल 3 घंटे का एक्सपोजर लगा के आ जा, करंट की वैल्यू कम कर दे और एक्सपोजर 3 घंटे का लगा दे, अपन बैठ के डिस्कशन करेंगे। देखिए बहुत सीनियर आदमी, गोल्ड मेडलिस्ट वहां के, और वो कह रहे हैं कि अपन डिस्कशन करेंगे। एक छोटा सा स्टूडेंट जो भी नया आया है उसके साथ में ये लाइब्रेरी जाते, एक ही राइटर की 2 किताब लेके आते थे। मेरे को आज भी याद है किताब के नाम, बीके अग्रवाल सर को भी याद होगा, और उसमें मेरे को आज भी याद है कि एक कांच के गिलास में एयर बबल आया हुआ और उसको किस तरीके से कि कॉन्वेक्स होगा कि कॉन्केव होगा, किस तरीके से वहां से साइंस निकालनी है। ये 1 घंटा ये पढ़ते थे और 1 घंटा मैं पढ़ता था और फिर दोनों डिस्कशन करते थे। ये रियल साइंस होती है जो एक सीनियर जूनियर को ट्रांसफर करता है, किस तरीके से आगे बढ़ता है। तो आप सबके लिए भी ये एक बहुत बड़ी अपॉर्चुनिटी है कि मेरे तो रियल गुरु मैं इनको ही मानता हूं, बाकी सब टीचर बहुत सारे रहे, मगर जिनसे मैंने सीखा कि किस तरीके से काम करना चाहिए वो यही है। फिजिक्स को जीवन में जीते हैं। मतलब जैसे मैं एक छोटा सा आपको एग्जांपल दूं, ये कागज है, ये सिंपल कहते हैं कि इसको सिंपल, इससे अपन क्या निकाल सकते हैं। देखिए मैं आपको एक छोटा सा एक्सपेरिमेंट करके बताता हूं जो इनसे सीखा हुआ है। मैंने इसको कागज का फूंक दिया, ये ऊपर आ गया। अब आपको इसको एनालाइज करना है कि ये ऊपर क्यों आया है, आपका ऑब्जर्वेशन होना चाहिए। इससे आप विमानिकी का, पूरा हेलीकॉप्टर का कंसेप्ट, अरबों खरबों रुपए की इंडस्ट्री निकाल सकते हो केवल इस छोटे से कागज के एक आपके ऑब्जर्वेशन से। तो जो रियल चीज सीखने को मिलती है, साइंटिस्ट से मिलती है, वो ऐसे लोगों से मिलती है। प्रोफेसर याकमी सर के बारे में तो मैं बहुत छोटा हूं कहने के लिए। इन्होंने भाभा एटॉमिक में जो काम करे हैं वो अनपैरेलल है और देश को इन्होंने खूब सेवा दी है और आगे भी अभी भी अपने आइडियाज देते रहते हैं। प्रोफेसर माइकल यहाँ पर हैं, इनसे भी हमें सीखने को बहुत मिलेगा। और यहाँ पे जो डिफरेंट कॉर्नर से जो साइंटिस्ट लोग आए हैं, बहुत बड़े बड़े प्रोफेसर हैं, जबकि मैं नाम नहीं ले सकता, उन सभी का बहुत बहुत अभिवादन करता हूं मैं। और उनसे मैं मानता हूं कि मुझको और यहाँ का जो ऑडियंस है उसको बहुत कुछ सीखने को मिलेगा। अगर यहाँ पे कोई इनकन्वीनियंस हो तो उसके लिए आप क्षमा करना, स्टे में कोई दिक्कत आए करे तो उसके लिए आप बिल्कुल, जो टीम लगी हुई है वो सब आपको कोऑपरेट करेगी, और फिर भी कोई होगी तो आप बताएं बिल्कुल। बहुत बहुत धन्यवाद, सभी का वेलकम।
Thank you so much, Mangal sir, for your enlightening words. Your insight has added a profound dimension to our conference, and we all know that your experiments of learning with doing and doing to learn are very well famous with all of us. Now it is my pleasure to introduce the Vice President of Condensed Matter Research Society, Dr. Mahendra Vyas, and also request him to come to the stage and offer his insights about our research society, CMRS, and its goals. Dr. Mahendra Vyas.
Very good morning to all of you. I welcoming you in ICC 2023 on behalf of CMRS, which is newly constituted research society, and it's fully dedicated to research work. Next. This society introduced in 2022 means just before 1 year, and our main target is to develop the scientific areas in all fields of science. We are Condensed Matter Research Society. By transferring science and technology, we promote all fields of science. Condensed Matter Research Society is working for popularization and promotion of scientific research. Next. It's basically motivates the students and young researchers to publish and present their research work in its research journal from 2023. Basically, it have two research journal. First is known as a Journal of Condensed Matter, and second is known as a Chemical Synthesis Letters. We will discuss later. Our society organizes seminars just like this, conference, international conference, workshop, trainings, and awareness programs of scientific communities. Our target is to cultivate and promote general science and its branches of science, to disseminate the knowledge of science and applications through meetings, trainings, camps just like this, and discussion and publication, to foster high standards in teaching and education of science. These are the objectives of our society, and we will run work throughout the years, or we can say throughout the time. Next. Next. This is basically brief details regarding our journal, Journal of Condensed Matter. This is related to physics journal, and it will cover all fields which are related to physics like structural, thermal and transition in equilibrium and phase, statistical mechanism and thermodynamics of equilibrium and non-equilibrium processes. For years back, it has also received their ISSN numbers, and in future it will be basically categorized in Scopus and any other agencies. These are the areas in which JCM will cover all kinds of fields, basically nanomaterials, material science, glass and ceramics, photonic materials and plasmonics, and we can get details from our official website of CMRS. This is our second, it will start very soon. Chemical Synthesis Letters, it will 100% peer reviewed and referred journal. It's for chemistry or chemical science branch. And after launching, just after a few days, we can get all kinds of information regarding this. In very short periods, means just like 1 year, we have done so many kinds of events related to this, and number first is known as a field visit of problem identification. It is from PhD department, public health and engineering department. By this process, we through visit a student learned how to determination of different parameters of water, chlorides, fluorides, nitrates, and it's basically specified for 20 students of MSc students of chemistry. It done by me as a organizer. Next, second. These are the photographs during the event, our first event. This event is organized on Science Day, which convener Dr. Praveen Prohit sir. Events basically just like a science quiz for promote the science education and students on Science Day 28th February 2023. Means starting of this year. Next. This is our upcoming program, International Conference ICC 2023. This is our brochure. You have seen earlier. This is our organizing committee, or we can say executive members of CMRS. Our, you know about Dr. Ravindra Mangal sir, who located in front of us. And these are our executive members. Secretary Dr. Manoj Singh Shekhawat is the secretary of this society. This is particular for membership. There are two types of membership. First for faculty membership and second for student membership. And number third is known as a honorary membership. Honorary membership is completely free for, and faculty and student membership is also available here, and you can fill the form. After the getting information on website, you can associate with us, and it's our wish to fulfill the all vacuum in front of us in field of science by this prestigious platform. Thank you.
Thank you, Dr. Mahendra. Ladies and gentlemen, esteemed guests, and all the attendees, as we move forward towards the successful conclusion of this inaugural ceremony, and as we pace towards the technical events of the conference, I once again extend my warmest greetings to all the people and the guests and participants who are present here today. And finally, I hand over the stage to Dr. Praveen Purohit, member CMRS Society, for the conduction of further technical events. Dr. Praveen Purohit, please.
Thank you, ma'am. Thank you for handing over the session. And it's really a very great moment that we are having this international conference being organized by Engineering College Bikaner under the banner of CMRS. And I hope everyone will find it exciting and fascinating. Now today we will be having keynote lectures and various other sessions regarding the technical sessions, oral sessions or poster presentation, etc. The schedule of which has been provided to each and everyone. Now we will be proceeding towards the keynote lecture. The keynote lecture here, it will be actually, the session will be chaired by Professor Biswas sir, Sampat Kumar Biswas sir. I will just read out a brief biodata, a biosketch of Professor Sampat Kumar Biswas. And Professor Biswas has done his MSc Chemistry with specialization in Physical Chemistry, University of North Bengal in 1973. This 1973 is really a very fascinating year for me, as it is my date of birth. So I am really feeling it very excited that I'm giving the biosketch of such a person when I was born. He was doing such kind of research. So he has done his PhD Science in University of Calcutta in 1983, postdoctoral from School of Material, University of Leeds, United Kingdom in 1990-91, and positions held by him was he was Chief Scientist, CSIR, CGCRI up to 2013, Professor at MNIT Jaipur 2014-2017, and Research Associate, Research Advisor at MNIT Jaipur in year 2023. Now, if you look at the publication, he has a publication of 70 numbers in SCI General, H-indexed 18, and he has 3 patents to his name. Now, if you look at the project supervised by him, he is the nodal officer, non-oxide based advanced structural materials for application in armor, that is a CSIR network project of about 14.6 crores. Now, he is the principal investigator in preparation and in densification of AIN powdered DST sanctioned project, rupees 33 lakhs. And he is a PI development of AIN armor tiles, DRDO, rupees 14 lakhs, and level 4. And for futuristic infantry combustion vehicle, FICV, ODC, Ministry of Defense, rupees 19 lakhs. And PI effect of microstructure on shock behavior of SIC ceramic for armor application, DRDO, rupees 38 lakhs. So his research interest, if we look into, is dynamic behavior of materials under high strain or weight loading, then multifunctional ceramic composites for different engineering application, non-catalyst gas solid reactions. If you look at his achievements, it is the development of ceramic armor was appreciated as a news item in Times of India, Ordnance Factory Board, Ministry of Defense and DRDO, and the members of professional association that he is associated with are Indo-British Professional Association, Material Research Society of India, and the Indian Ceramic Society, that is IS. So it was only a brief bio sketch of Dr. Bishwas, and I hope it's not very, you can say, it's very brief, and when we will have the interaction with him, then we will come to know more about him. And now I will also give a brief sketch of Professor Narendra Bojak. And Professor Narendra Bojak, he is presently working as a professor green chemistry research in the PG Department of Chemistry, Government Dungar College, which is A grade in MGS University, and 26 students has completed MPhil and 21 students has completed PhD under his supervision. He is the member of BOS Bikaner University, member research committee, and member of the Ceramic Council, Bikaner, the Academic Council, Bikaner Technical University. He has delivered about 90 invited lectures in international national conference being visited at Washington DC, USA, Abu Dhabi, Austria, and Nepal. He has organized about 15 symposium, workshop, conferences, and research areas are green chemistry, food and drug analysis, and he has developed the Smart Science Lab based on augmented and virtual reality. Now, I invite both of them to carry out the session as a chairman and the co-chairman of this. So, I kindly invite them to this dais and carry out the proceeding of the session. And I will hand over the session to the chairman and the co-chairman. Thank you, sir.
Students, faculty, and distinguished guests. No, no sound? More loud? It's okay? Okay, thank you, thank you. Now this session starts with the lecture of Professor J.V. Yaki. He is a very renowned person, and he was an ex-associate director of BARC, Bhabha Atomic Research Center, Mumbai. Professor Yaki, I know him since a long time, and he has been working with several areas in the condensed matter. So I would like to request him to kindly deliver this keynote address to us. Thank you, Professor.
Okay, good morning. Welcome everybody to my talk. As I was saying, it is a very general talk, meant mostly for my younger friends. The title also you can see is Points to Ponder for Success in Scientific Research. Sorry, I'll be sitting and giving a talk. I can't stand for a very long time there. Next. Now somebody has to operate it now. Who will operate? I give a list. See, I'm not the first one to speak on such topics. So many big fellows have already spoken and written books. Among them, you will see there are 2 or 3 Nobel laureates. Physics, you can see immunologist, mathematician Hardy, neuroscientist, Nobel Prize winner Kahel, and similarly Feynman. They have all written books how to succeed in science, and they are aimed at young fellows. Before we talk all that, I hope people can read whatever is written. What is science? We want to talk about how to succeed in science. Before that, let us broadly think what is science. When you do science, you are basically trying to answer a question. Is this material a liquid crystal or not? Like that. So you start working on it in your physics lab, chemistry lab, biology lab, wherever you are. You try to make, and when you say you are studying it, a sample, you are making some observations, then making a plot or a graph sheet of that, and then trying to see does it form a pattern? Is it a linear thing? Is it exponential or whatever? So you make careful observations and patterns lead. अब क्या होता है? आप एक क्वेश्चन का जवाब देने निकले थे. Sorry, Michael, I switch to Hindi sometimes. So एक सवाल का जवाब देने निकले 10 सवाल और पैदा हो गए. But that is research. Research है यही. A good question, if solved, can lead to new discoveries. That's how new discoveries are made. If you succeed in answering a new question in a new way. So discoveries lead to patents. Patents lead to innovations. Innovations lead to prototypes. Useful commercial products. New technologies for health, medicine, environment, energy. That's what everybody talks these days, that you should work on these areas. And entrepreneurships and jobs. You see, 99% of the people are doing science because they think they are going to get a job in that area. If you already know you are not going to get a job, you will not attend to that kind of a subject. So that is needed. And jobs needed means you need a multidisciplinarity experience. I am going to dwell on this topic more and more. I am giving an example. I retired long ago, but 2 years ago I wrote a book for a British publisher that is on superconductivity. Now I am writing a book on employability for PhD students in STEM. STEM means science, technology, engineering, mathematics, also medical. Then you can write double M. So how to do that? All over the world, chat GPT, so many things are coming and disturbing your mind. Will I get a job or not? So to start with, let me say in this audience, there must be some fresh PhD students or who are going to register now. Doing a PhD thesis work is very tough job. वो जिसको बोलते हैं ना, बहुत जालिम चीज़ है PhD करना, बहुत मुश्किल है. जब करने निकलते हो 5 साल लगते हैं, उसमें बहुत मेहनत लगती है. You have to collect a lot of original data. आपसे कहा जाता और डेटा लेके आओ और लेके आओ. And then before that they say, look for a good problem in research. अरे वो good problem क्या है ये तो बता दो. So your professor, no, this is not enough. So then they say you should publish minimum 4 to 5 papers before you submit your thesis. और उनमें ज़्यादातर आपका नाम फर्स्ट होना चाहिए. बहुत सारे लोग ये कहेंगे. पर क्या आपके प्रोफेसर वो अलाउ करेंगे? वो ये भी मुश्किल है. तो मैं कहूँगा 5 में से 3 में हो तो बहुत अच्छा है. ये ठीक है. फिर आपको लिखना आना चाहिए, आपको अपना थीसिस सबमिट करना है, आपको पेपर्स लिखने हैं. And worst part is you have to appear in a viva voce test. I have conducted dozens of vivas all over the country, even once or twice abroad in Germany and all. You know, that is the lowest confidence day of a candidate when he has to publicly defend what he did for the last 5 years. So there are reasons for that. You can discuss with me later because time is short. Then you are starting looking for a job. Your job could be academic, in teaching, or in research, or sometimes in industry. In all these topics you can have all kinds of jobs. होता क्या है, आप 5 साल एक यूनिवर्सिटी में रहे, वहाँ आप उस डिपार्टमेंट में रहे, आपको लगता है मैं भी क्यों इन जैसा नहीं बन जाऊँ, ये आसान है, इंडस्ट्री में कौन जाएगा. That also is there. So like all creative fields, painting, art, music, writing, poetry, research also needs a lot of hard work, tenacity जिसको बोलते हैं. Are you listening to me? Tenacity. Hello? वो पीछे वाले लोग. So tenacity, you need dedication, determination, diligence, resilience. मैंने 5 वर्ड बोले हैं. Tenacity, resilience, determination, dedication and diligence. अगर मैं इसमें एक और वर्ड जोड़ दूं, frugality, frugal living, तो ये गांधीयन फिलॉसफी बन जाएगी. महात्मा गांधी यही 6 चीज़ें करता था, और विदेश में इसको गांधीयन फिलॉसफी बोलते हैं, बट इन इंडिया वी कॉल इट इंडियन फिलॉसफी बिकॉज वो गांधी भी तो अपना ही था ना. सो एवरीबडी ऑफ अस हैज ए लिटिल बिट ऑफ गांधी ऑलरेडी इन अस. सो you already have a template for success in this world. You are way ahead of other countries' people, students, because you have a little bit of Gandhi in you. But the thing is, you have to do well. How to do well? You must think originally. I'll give you an example. Allahabad में एक इंस्टीट्यूट है, हरिश्चंद्र रिसर्च इंस्टीट्यूट, छोटी सी मैथमेटिक्स की है. इट इज़ नाउ वर्किंग अंडर डिपार्टमेंट ऑफ एटॉमिक एनर्जी. वहाँ एक स्टूडेंट था बहुत साल पहले, 30-40-50 साल पहले, हरिश्चंद्र. वो एमएससी फिजिक्स का एग्ज़ाम था. सीवी रामन केम एज ए एग्जामिनर. So C.V. Raman had not declared the question paper before he came. He was a Nobel laureate. So he wrote 6 questions, copy बना के सबको दे दो. There were some 20 students. They were given 2 hours. Now this Harishchandra attempted the toughest question, which was related to a music instrument. Raman was fond of that. Write the equation of that, frequencies and all that thing. He attempted that. पर उसमें उसके 2 घंटे चले गए. Whereas all the other people attempted the other 4 questions which were simpler, and so the question answer sheets were given to Raman. Raman gave 100 out of 100 to Harishchandra. He says, जो बंदा ये कर सकता है वो कुछ भी कर सकता है. So try to be original. Don't be afraid. Have confidence. So that is now it is called, that institute is named after him. So जब आप रिसर्च करते हो, पीएचडी की रिसर्च करते हो, तो आपके आगे बहुत सारे चैलेंजेस हैं. वो चैलेंजेस क्या हैं? हाँ, छोड़ दो. एक तो आपको राइटिंग आना चाहिए, पीएचडी थीसिस. जब लिखने लगते हैं तो पता लगता है उसमें आपकी जान निकलती है. एवरीबडी विल से दिस इज नॉट हाउ यू राइट, बट दे डोंट टेल यू हाउ टू राइट. That also is the problem. So लिखना आना चाहिए, और लिखना अच्छा आना चाहिए, और आपके publication should be of high quality. High quality means what? मैं एक एग्जाम्पल दे रहा हूँ. एक PhD स्टूडेंट था टाटा इंस्टीट्यूट ऑफ फंडामेंटल रिसर्च में, E.V. संपत कुमारन. He later became dean of faculty of TFR. He used to work out for his PhD. जब उसने PhD सबमिट की TFR में, उस PhD वर्क के साथ 25 फिजिकल रिव्यू पेपर लगे हुए थे. 25 physical review papers. I know that. So then you should know how to write a manuscript for a journal. ये भी बहुत मुश्किल काम है. How to write your CV. अरे CV तो सबको लिखना आना चाहिए. लोग एक दूसरे का कॉपी कर लेते हैं. उसका CV ऐसा तो मेरा भी ऐसा होना चाहिए. No, don't copy, write originally. Then CV और resume में फ़र्क है. CV is meant for academic jobs and all that. मैंने इतने पेपर पब्लिश किए, मेरे इतने लेक्चर हैं, ये है वो है. पेटेंट हैं. When you apply to industry, it is a resume. उनके लिए 40 पेपर हैं कि 20 पेपर है, कुछ खास फर्क नहीं है. They are looking for something else, industry people. That is a resume. So learn about it. Then you need a covering letter which you don't write, somebody else writes for you. And which he may be your professor or your professor's competitor. हो सकता है आपके प्रोफेसर की जिससे नहीं बनती वो आपको लेटर दे दे, ये भी पॉसिबल है. Then writing a research proposal for DST funding and other funding. Sometimes you get a postdoc appointment on the strength of having secured funds already from a funding agency for your project, although you don't have a job. So that also is possible. So, and in जिंदगी में उन 5 सालों में आपके खास तौर पर इवन बाद में there will be lot of bad opportunities. You will have bad shallow points in your life. That does not mean आप बैठे रहो कुछ नहीं करोगे मेरा काम तो ठीक नहीं चल रहा है. That is the golden period to learn new skills. I did it myself in BRC for years together. I am telling you, as a physicist, I was in chemistry department. I learned glass blowing. I learned how to wind a furnace. I can wind a furnace today in 1/6 of the price which you pay for a standard marketing furnace. Then I learned spot welding, soldering contacts, designing a glass cryostat, liquid nitrogen, liquid helium. Use of vacuum equipment, using a vacuum line, working on a lathe, go to workshop and work on a lathe. Now you will say you were in BRC, so you had all the opportunities, you learnt all that. I think there are different people have different opportunities, so you should try to. Then can you innovate even in your bad patch? I made India's first high resolution electrical resistivity equipment which could resolve 1 nano ohm. When I made, there were no digital voltmeters. I am talking of 1972. There was no digital voltmeter that time. So even if you have a bad period, your day will come. Just hang on, learn more things. You will be more competitive. And then I am telling some very general things. आपको अच्छी लगे या कम अच्छी लगे, मेरा तो फर्ज है आपको बताना कि मैं क्या कहना चाहता हूँ. जब when things are in your control, you got a PhD, you are starting your career, or maybe you are a postdoc, you are a professor, try to work with world's best experts. See, rather than working with a colleague who is like you, not bad. If you are not doing anything else, it is okay. But can you choose to work with the world's number one? I am giving examples. There is a Professor Alan Herman. He is a professor of physics, also of music. He is in Colorado Boulder. Even now he is there. I told him, you work on thallium superconductors, we also work. Shall we edit a book together? I impressed him so much in a conference in USA. I gave him everything written. Which are the chapters? Who will write the chapters? And if that one person says, no, I can't, then who is the second best, third best? उसको इतना मसाला दे दिया, he could not say no. So we did that. That was in 94. Yeah, sorry. मैं ऐसे चलता रहूँगा. So, secondly, the world's famous spin glasses expert, he called me to spend 6 months in his lab, Ian Campbell. Actually, the Nobel laureate who did GMR work, Albert Fert, he was his student next door. And similarly, so I went and worked with him. Then in chromium magnetism, I am talking of physics, so spin density wave antiferromagnetism in chromium. There too, I chose the world's number one in University of Toronto, interacted with him, impressed him, did other things for him before he said, oh, yes. So I wrote a Reviews of Modern Physics article, 105 pages long with him. Reviews of Modern Physics is the topmost physics journal with the highest impact. There is no other physics journal in you name it. Even PRL comes much behind. Then finally, I wanted to start new topics. New topics means I was from chemistry department, but I had shifted to physics. I was inherently a physics person. So why not work on something where both the things are used? Organic magnets. So molecular magnets. I started. So I again looked for who is the best. He was in Bordeaux, France. I chose him. So we did a big project together. And this is how you have to, chase people, chase to do things. How many more minutes I stop? 1 minute. Okay. Next. Oh, he is the world's best. Now this 1 minute will be going on this only. 500 years ago, he was the best scientist, best painter, best engineer, best botanistic capabilities. You name, he did everything. He's लियोनार्डो दा विंची, नाम सुना होगा, जिसने मोनालिसा पेंट की थी, पर उसने दुनिया में बहुत से काम किए. मिलान के राजा ने उसको बुलाया, इटली मिलान. He said, plague is coming every year, half the population of Milan is wiped out, will you come and do something for us? So he shifted there. He designed the whole city once again. King of France, he was a young fellow fond of paintings. He asked Leonardo, can you shift to France? He was already old. After 2 years, Leonardo died. Now, can you come here? I'll give you a chateau. Chateau means a किला. आपके लिए एक किला सुरक्षित है. आप यहाँ आइए, आपको अच्छे पैसे दिए जाएंगे, आपको कुछ नहीं करना है, सिर्फ यहाँ बैठना है. वो हमारी इज्जत का सवाल है. He came, and those days, how did he carry Mona Lisa? गधों पे, ये खच्चरों पे, टट्टुओं पे लेके गए, क्योंकि there's no other way to carry. Only on mules he carried it, all the paintings. He stayed there for 2 years, and he had a big name. I stop here. I have a lot of things to tell you, but then time is limited.
Although he is a man of condensed matter physics, he has got many laurels in his chest. So those are, I just mentioned 1 or 2 points. One which I liked very much is that he has got 102 articles in his possession and is very high Google citation index. Apart from, because those are the criteria we look for. And I thank Professor Yaki for his nice presentation. And if anyone wants to ask, I'll request.
Thank you for introducing me to this audience. Let me say, ये जो मेन पिक्चर है, ये मैंने फोटो क्लिक की थी स्पेन में, एक सिटी है वालेंसिया. देखो लोगों को कितना दिमाग में उथल पुथल है, कितना काम करना चाहते हैं. People made this sculpture out of wooden strips. It will be burnt on the last day like Dashera, our festival. But it is more than 3 stories high, and it shows all the kind of things which he did. And last में उस तरफ है एक छोटी सी पिक्चर मोनालिसा की. जब मैं जिंदगी में फर्स्ट टाइम पेरिस गया, I clicked it. I have a aim and shoot camera. It won't give me a picture. So I put the flash on. You are not allowed to put the flash on. There is a security fellow, police fellow standing there. If you do, he'll arrest you. I did it, and I was not arrested. Thank you.
Thank you, sir. Thank you for your ideas and the knowledge that you shared with these young researchers and the professors who have visited here. Now, I hand over the session. You may invite the second.
Okay, now I would like to announce that the next speaker is Professor Michael De Loro or Michel De Loro. Michael De Loro. Right. So, De Loro, yeah, please. And he is a man in the neurophysiology area and communications. And he has done his, apart from his academic activities, his PhD course in molecular and regenerative medicine. That is a very interesting area now. He specialized in the fabrication and characterization of the modeling of operational principles of organic electronic devices. Currently, his research activities focused on the clinical validation of implantable organic electronic device. There is a very important area. I hope everybody will be interested in his talk. So I would like to request Mikhail to kindly present your activities. Thank you.
Okay, so good morning. Good morning, everyone. I am Michele Di Lauro, and I come from the Center of Translational Neurophysiology of Speech and Communication in Ferrara, which is held in this beautiful historical place. It's a center from the Italian Institute of Technology. But as a background, I am a chemist. So this talk is going to be the story on how does a chemist be useful for the neurophysiologist community and for the medicine community, and how this is made possible by the physics of condensed matter, and in particular by the physics of organic semiconductors. So I would like, okay. So I will tell you a bit about my story, okay? So first of all, I'm lost in translational. Okay, this is a word pun, but it's great because what we do in our center is to work to develop translational technology. So we want that everything that we develop is capable of being translated to the human being in clinical scenarios. Okay? And translation by itself, by definition, as Sofia Coppola, the director of this film, said, is the story about things being disconnected and looking for moments of connection. And this is what we are doing with, let's say, with organic electronics, because we want to bridge a gap which is between the biological world and the electronic world. Okay, so integration between electronic devices and living matter, in our case, the central nervous system, requires bidirectional communication. But there is a lot of mismatch, because there is a mechanical mismatch, there is a structural mismatch, environmental mismatch. The carriers are different. The time scale are incredibly different. So we want to bridge a signaling gap between the living matter, let's say, and the electronics. Can we bridge it? Of course, this is not an idea of mine. We can do it with organic electronics. I reported here some very famous papers that are dealing with this concept. But the core of this bridging relies in the materials that we are using. We are using these organic mixed electronic conductors. And here I present you P.PSS, which is the workhorse of this field. Okay, it's a copolymer. It's made out of two complementary ionomers. So one is positively charged, is this polyethylene dioxide thiophene, and the counter ion basically is this polystyrene sulfonate. Okay, so what happens is that this polymer is neutral by itself, but it has the capability of conducting charge. If I apply a bias, what happens is that I have the transport of positive charges in the polyethylene dioxide thiophene chain, which is counterbalanced by an opposite motion of protons in the polyanion complementary chain. Okay, so the holes that move are dressed with this negative charge that goes along with them, given by the motion, the counter motion of protons. Okay, this is the point. This guy is a conductor. It means that it obeys the Ohm's law. Okay, but what happens is that I can modify its conductivity. Why? How? By intercalating cations. Because if I drive cations in this polyanionic matrix, what happens is that they will coordinate the sulfonate ions, and then the protons will not be able to move, and then the conductance changes. The conductance drops. Okay? The resistance increases, and this behaves as an organic semiconductor, which is the main architecture that we use for exploiting these properties. Is the organic electrochemical transistor or the electrolyte gated organic transistor, you call it whatever. But the important thing is that in these devices, electronic conductivity depends and varies with ionic concentration, and in this way the organic mixed ionic electronic conductors can bridge the signaling gap. Okay? Also, they are organic. So we are chemists, we can tailor the properties by design, we can make them biocompatible, biodegradable, and also mechanically compliant, let's say. Okay, I was telling you, this is the main architecture. It's the three-terminal architecture in which a channel of polymer between two electrodes, which are called source and drain, has a modulable conductivity, which is modulated by the potential that I apply to a third electrode, which is bathing in the solution, and drives cations into the film. So this is what we are doing. And you see, the ion density in proximity to the channel governs the conductivity. Small gate voltage modification yield great current modification, and the transconductance, which is namely the derivative of the channel current with respect of the gate voltage, is the key operational parameter because it's the gain factor of our devices. Okay, but all these quantities are are quasi-static. When we want to approach the brain, we want to collect, analyze, and let's say describe signals that are varying with time. And so the dynamics of the device response and of the material response becomes critical. And typically our organic devices are very slow, and so we need to always to choose to make a compromise between having a decent bandwidth or having a decent, let's say, transconductance amplification. And so we invented a field in which slow is good, and we called it the organic neuromorphic electronics. Okay, neuromorphic means that your circuit can emulate the signal processing features of the human brain, okay, of a neuron. Okay, but how do neurons work when they are processing the signals? Well, they are relying on kinetic imbalance between the input signals and the output signals. So what is the easiest way to emulate this behavior in organic electronic device? Well, nothing is as simple as that. I take an electrolyte, it has got an ion and cations inside. On one side, I have my organic conductive polymer. If I apply a pulse of voltage, I will cause the ions to migrate, okay? I have this current, the current of cations, which is the displacement current. You know it better than me. And what happens is that when I remove the stimulus, the system relaxes, okay? So if the subsequent stimuli are far enough, so the system can fully relax, and the second pulse arrives in exactly the same situation as the first one. Okay, but if the pulse frequency is too high, the system cannot fully relax. So when the second spike arrives, I have less displaceable cations, so I have a lower current, and I have, let's say, a profile of evolution of current in time, which is a time frequency integration, which is what neurons do when they operate. The entire phenomenon is called short-term plasticity, and this is very useful technologically. Okay, so how can we control this kinetic imbalance? Okay, this is, of course, controlled by capacitance. So it's controlled by device geometry, by polymer thickness, polymer nature, let's say polymer chemistry, and also parameters of the electrolyte. So concentration and eventually specific interaction between some solutes and our electrodes. Okay, so a given combination of these parameters yield one single time constant upon one single frequency of stimulation. But we want to keep in mind the original mission. So we want to be translatable. And when you are designing a device for biomedical application, you cannot change neither of this stuff, okay? Because in order to get approval from your ethical committee and from your Ministry of Health to put something in the brain of people, you need to define the architecture very precisely, and it cannot change anymore. So we had to devise operational routes to tunable neuromorphic performance without altering the geometry, the thickness of the polymer, and whatsoever, okay, the materials. And we can, this is the start of our story. It's a quite long story. It started during my PhD, so now almost 10 years ago. And what happens is that we learned at first how to control the short-term plasticity by changing the material. Then we discovered, and this was inspirational, that the time constant of our STP decay profile depends on the concentration of the analytes in solution. And so we used it for sensing after proper, let's say, development of analytical circuit models for our devices. And then we went on because we said, okay, all of these were two-terminal or pseudo-two-terminal architecture, but we are working with a transistor which has got 3 terminals. So let's try to make advantage of all the available terminals in our architecture. And now I don't want to bother you with all the mathematics, but the important thing is that we managed to elicit tunable STP decay, tunable short-term plasticity in our devices, either by acting on the gate voltage offset or by acting on the frequency of stimulation. Okay, so we liked it because we have seen, let's say, that the parameter that the neuromorphic behavior depends on the gate voltage as exactly as the transfer characteristics of our devices. And so we went on. Okay, the important take-home message of this is that we have in our toolbox a frequency-dependent resistor whose dependency on frequency depends on the doping state, which is the resistance. I know it sounds a tongue twister, but it's important to understand this, okay? So there is a complex interplay because we have the dynamic of the double layer in between. So ion dynamics governs resistance, which governs frequency dependency of our architecture. Okay, we went on with this. We tried to change a lot of different connection scheme, and we managed to eventually reach a configuration which one can elicit at will depression and potentiation. We can alter, of course, the baseline current, and we have relative current variation for the doped channel. Most importantly, by setting an arbitrary reading time, we can deterministically predict the relative current variation, which is linear with the gate voltage, and we as physicists, we like linear trends, and so we can bring these small devices, which are memories, we can bring them in different states, and the memory state depends on the gate voltage. So this is very useful. Okay, so now we add a line to our tongue twister, which is the gate voltage, so our main control parameter. But now, what do we want to do with this? Because we are working in a electrophysiology department. Okay, so we are using it to filter electrophysiological data in real time. So this is when we interface our electrolyte-gated organic transistor with a simple electromyography experiment. And you see, these are the spectrograms of the trials of electromyography. This is actually a PhD student holding a weight into his hand with some electrodes attached in his muscles. And this is the average spectrogram, okay? You see the content in frequency is all around 20. Okay, but what we want to do, if we are building a, let's say, human to machine interface, and we are focused on electromyography, we want to isolate this 20 Hertz frequency with respect to all the others. And we can do it. We can do it because with our gate voltage, we are able to increase the relative power of a single frequency band with respect to all the others. So now this is a sorting efficiency map centered on 20 Hertz, so I can transduce the 20 Hertz way better than the high frequency, and also better than some low frequency, which is the discovery of this work. Okay, but now that we have understood that the dynamics of the double layer is a key operational parameter to device filters, now the fantasy is the limit, because we can build up organic resistors, we can build up organic electrolyte capacitors, and we can engineer filters with these guys. RC filters, normal passive filters, okay? And this is what we have been doing lately. So we are connecting electrolyte-gated organic electrolyte-gated organic capacitors and organic resistor in series, achieving low pass and high pass filters. And if we couple these with the electrolyte-gated organic transistor, which is inherently a low pass filtering guy, we can achieve band pass and modulable low pass. Okay. And we can also implement this in, let's say, convoluted architecture, in which we are able to sort a common input signal, but just, let's say, transducing the high frequencies on one side and the low frequencies on the other side. This is very important for brain-machine interfaces, because sometimes you have a very convoluted input signals, but you are only interested into the spectral component, like around 8 Hertz, for example, in epilepsy. Okay, in epilepsy you want the activity at 8 Hertz. All the rest is noise. So with some kind of architecture like this, in principle, in the future, will be possible to route the signals to have the 8 Hertz component on one line, the 20 Hertz component on the other line, and it's all engineering of organic conductive polymers. So this is a job for us. Okay. Sorry. Okay. Of course, it does work to factorize also electrophysiological signals. So this signal over here is a somatosensory evoked potential in the cortex of a rat model. Okay, so we displace the whisker, and this gives rise to a very high potential in the motor cortex of these animals, and we can factorize it with our architecture. We can send the alpha band on one hand, the beta band on the other one, and some mixed, let's say, configurations. Okay, so this was one idea, the idea of filtering, exploiting the dynamic of the double layer. The other idea that is enabled by this neuromorphic performance of organic polymers is that if they present a specific interaction with some analyte in solution, we can exploit the time evolution of our short-term plasticity to quantify the analytes in the solution. So this is the story that started in 2017. So the STP decay profile depends on ion dopamine concentration. And we can translate this concept in implantable architecture by using deep brain electrodes. These are 80 micron wires that are thought to enter the brain, okay? We can electrodeposit our conductive polymer on the tip by electropolymerizing the monomers. And okay, so we thought it was a piece of cake. So let's measure dopamine in vivo. Okay, it was not a piece of cake, or at least it was the most difficult cakes in the world, because when you enter the surgical room, there are plenty of other problems, because you have additional ground reference. The patient cannot be grounded, for example. And also, you cannot elicit dopamine production by electrical stimulation, because otherwise you will destroy your conductive polymer. You will oxidize it. And so we came up, actually, a brilliant PhD student of mine came up with this architecture. Let's say he reduced the dimensionality of the problem up to a single wire, as if it was a normal working electrode in an electrochemistry experiment. Just pulse it and measure the displacement current in that terminal. Of course, you need a source measure unit to do this. You cannot do it with a normal, let's say, potential stat. But the point is that you can emulate this STP, which is now very resembling a pulsed chronoamperometry. Okay, you can measure the envelope and extract the time constant of your profile, and this actually correlates with the concentration of dopamine in vivo. We did not elicit it by electrical production, but we just carried out a controlled penetration experiment. So you start from the motor cortex of rat, and we go inside with this very, very thin wire that you can see in this picture. I don't know if you can see it, but okay. In the red picture, there is a thin wire. Okay, so you start from the motor cortex, so no dopamine at all. Then you enter the corpus callosum, you have an outburst, and then you enter the substantia nigra pars compacta, which is almost linear increase of dopamine while you're doing your penetration experiment. Okay, so now up to the translational perspective, we are actually developing, and we have developed and authorized by the Italian Ministry of Health, which is a painstaking authorization. We have developed this array of monoelectrode units, let's say. This is a multi-electrode array which can be operated either in recording or in stimulation or in neuromorphic fashion or as transistors, to be placed on the cortex of humans undergoing surgical removal of, let's say, cancer in the cortex of the brain. So, of course, what we told the ministry is that we want to cover the with P.PSS the electrodes of a neural array to improve the signal quality, because you increase the capacitance, you lower the resistance, and so this will increase your signal to noise ratio. But of course, this is an excuse, because what we want to study is to improve the spatio-temporal resolution of our transducing capabilities by testing a number of different architectures. So we can improve, let's say, spatial resolution by crowding the array with the recording position, and we can improve the temporal resolution by testing different aspect ratios of our channel, which determine different capacitance, which determine different double layer kinetic. It's always in there, the solution. Okay, so in conclusion, what I wanted to convey you, and I hope that I did it on time, 5 minutes, so we have plenty of time to chatter later. In conclusion, I hope that I conveyed you that OMIEC-based devices, so organic mixed ionic electronic conductor devices, can bridge the signaling gap between the biology and the electronics world, because they are slow and because they are dependent on ions, as me and you. So we are machines, electrochemical machines, that work on ion and are super slow and very low power, okay? So we need organic electronics to bridge this gap. Thanks to hysteresis, let's say, asymmetry between doping and anti-doping phenomena, these devices are inherently neuromorphic. They are sensitive to ions, so they can be used either to sensing of electrical, let's say, perturbances, or to sense some molecular moieties that I want to have in my solution, okay? That I need to achieve precise control of these time decay phenomena when I'm designing my transduction platform, and I can achieve this control by acting on the architecture, on the operational parameter, and on the connectome. So on how do I address and how do I interrogate my system. And the most important thing is that the time-frequency integration provided by neuromorphic organic electronic devices opens up unprecedented possibility in terms of real-time signal processing and filtering, which is, to our interpretation, the key towards more efficient brain-machine interfaces. But this is not the sole application possible. So your fantasy and our fantasy in envisioning future application is the limit, because the field is very young, and so anything that comes up to your mind is very likely that nobody has done it before, and so everything is a discovery, everything is a good paper. If we can do it together, it will be a nice field. Okay, in conclusions, I want to thank all the organic neuroelectronics group, especially, of course, Professor Fabio Biscarini, which allowed me to be here today. This is the entire group. These are the researcher and postdoc. These are the PhD students. This is the organic electronics line. We work together with the people in neurophysiology that are led by Professor Luciano Fadiga, always in Ferrara. I want to talk the entire organizing committee, and especially the person of Dr. Manoj Shekawat, which made everything for me to be here, and you for your kind attention. Thank you.
Thank you, Professor Loro. Just one or two short questions, please. From the audience, just one or two short questions, please. Yeah, please, stand up. Introduce yourself and ask.
Hello. Hi, sir. It is a very nice presentation. This is Dr. Penchalaya from VIT University, Vellore, from Tamil Nadu. I would like to know the devices what we develop. What is the mobility of the device? Moreover, they are organic materials you are using for neuromorphic electronics purpose. What is the mobility of the device?
Okay. So the mobility is quite an elusive concept in this architecture, because in order to extract the mobility, you need to perform a transfer characteristic. You want to fit it, but you want to know a value for the capacitance. Okay, and the capacitance of these hybrid, let's say, very wet electrodes, it's not precisely determined. It's not like we have an OFET, you know, a thin layer of silicon oxide. You see, okay, this is 17 nanofarads per centimeter square, or 14. So we do not have this precision in the determination of the capacitance. So it's difficult for me to give you a number, okay? But I have to say that the mobility, let's say the estimated mobility of P.PSS is usually very, very high. It's like 1 or 2 centimeters square per volt second, okay? Which is 100 times or 10 times more than the best pentasyn we had 10 years ago. So, but I have to say that these numbers are fake, okay? Because they do not take into account the real value of the capacitance, which is the capacitance of a porous electrode, hydrophilic one immersed in an electrolyte. So in our field, we never talk about mobility. We talk about differential transconductance, which is the product of mobility time capacitance, which is something that you can extract unambiguously from the transfer curve of your devices. And this is a number in Siemens, and it's easier to handle, let's say.
Great conversation and great job by Michelle. I would like to make one query and one comment here, particularly for the students. If you have carefully listened this lecture, you would have imagined the sulfate ions, organic semiconductors with respect to dopamine. and the question which has been asked with respect to mobility, it should be surpassed with respect to immobilization of the polymeric characterization. If they are doing the polymerization, immobilization, then there is no chance of mobility. But when you are going for the in vivo study, here my question starts. When we are going for the in vivo study, we will have to concentrate on the sulfate ions, particularly they are using the SO3 minus 1 as the immobilized part. So that becomes the more effective in case of dopamine. As a student, if you go for the structural part of SO3 minus, immobilized one and the dopamine, you can concrete the in vivo studies. But when we are going for the in vivo part, can we really find the effect of the, or the measurement effect of the SO3 on the mesomerization of dopamine? Because whenever you are taking some deep sound of sleep, you are getting some dopamine here, and this is why the in vivo studies are significant. So before he starts, I must congratulate that this is the next generation work. We will have to go with respect to the chemical science immobilized and the condensed matter physics.
Exactly.
Thank you very much, Michelle. We can go for the lot of discussion on this, and lot of collaborations are ahead. But your sense of dopamine retrogression with respect to SO3 minus is enormous. I must congratulate you for that.
Novel area. So, thank you very much. Now I would like to present another eminent speaker, Professor Sampath Raj Bhadera. Fortunately or unfortunately, his name is same with me, but I know him for a long time, and just I want to introduce him with you. He is now working as a professor in IIT Jodhpur since 2018. He has done his post-graduation from University of Jodhpur, and then he did his PhD doctoral research in on Mossberg spectroscopy. He joined DRDO long time back, and it's quite interesting that after that he joined academics as a professor in Department of Physics, IIT Jodhpur. Now his area of research are basically on multifunctional materials or functional materials like conducting polymers, ferrites, nanomaterials, materials for camouflage and field applications. He has published 75 research papers in international journals and has got 13 patents to his credit. So he has also written a chapter in the Encyclopedia of Nanoscience and Nanotechnology, published by the American Scientific Publishers, USA. So he is a life member of various important professional societies like Optical Society of India, Magnetic Society of India, Indian Association of Radiation Protection and Nuclear Track Society of India, and Council for Materials Research Society of India. He was a member of MRSI as well. He has represented DRDO to several countries like Canada, Belarus, Sweden, Brazil and USA. His current areas of research include rare earth-free magnet materials, max phase materials and maxings. I presume this is also an area where Dr. Kamath was working in DMRN.
Kamath, yeah.
Okay. Okay. So I would request Professor Bhadera 25 minutes.
Thank you, Chairman. Once again, I am before you. Thanks to Manoj. Thanks to colleagues here in Bikaner. Well, I'm out of this research work for last so many years, mostly doing administration. So might be this is work which we did over last 30 years plus, along with my colleague scientists in DRDO, and most of those scientists also did PhD with me. So it is their work I am presenting, and nothing much of mine in this one. But very important thing which I want to highlight here, the title is Magnificent World of Materials. Really, materials has got magnificent world. Right now, Michel has talked about, again, materials, to neuroscience, neurology, human-brain interaction, all those kinds of things. So you think of the area, and materials are very important. And another thing is, Dr. Yaki sir has mentioned something very interesting is, may I have your attention please? Okay, please, hello. May I have your attention please? Yeah, please be in the lecture. What I was trying to say is, Professor Yaki mentioned something very interesting is, when you do the research, focus is very important, observations are very important, you have to think about and how things can emerge if you are really having keen observations. And most of the results which I am going to present are observations only. Many of the things are purely observations, many of the things are innovations. Another point which we kept in mind while working, being in DRDO, most of our work had to be applied in nature. When you say applied in nature means they have to be simple methods of making it. They should be scalable. You should be able to make in large quantity. Like some of the materials we were making in kilogram. When I say nanocomposite, we started making in kilograms. Conducting polymers, we started making in kilograms. Ferrites, we started making in kilograms. Because if you don't make in those quantities, they cannot be used for real life applications. And more so when you scale up, how do you manage the properties and how do you manage the consistency of the properties, reproducibility of the things. But I'm not going to talk about those things, but these are things which are very important when you want to do the applied research. Currently I'm at IIT Jodhpur. First work I am talking about in nanocomposite of metal oxides. This somewhere we started in 93. We were having very meager facility, and perhaps one of the facility was Mosbar, and that was my PhD topic. So we thought that we should start working with materials containing iron. And we started thinking and we developed some material. And when we studied its Mosbar pattern, oh, it's not there, but then it showed relaxed spectrum, which indicated that this can be a small size particle, and that time the term was being used as ultra fine particles, and I had lots of paper studied on ultra fine particles. Some Swedish group was there, and then but we didn't have any facility. So I went to SSPL Delhi. One Dr. B.B. Sharma used to be there. I took that material and we took XRD spectrum, and then broad lines were there. So I was not really aware of XRD also that time, but Dr. Sharma mentioned that broad lines indicate small size particles, and based on that line width we calculated particle size to be 50 nanometer. So that was an accidental discovery of making nanoparticles, nanocomposite material, and this material we made in kilograms. So 5 kg base scale we made this material. Another work was one of my colleague. He wanted to do PhD. So he said that I want to do PhD from IIC Bangalore. We had interaction with one Professor T.R.N. Kutty. He was there in IIC Bangalore. And he said that I want to do PhD from IIC Bangalore. We were in Jodhpur. I said, why don't you do your PhD from Jodhpur? How does it matter? But he thought that IIC Bangalore has got much better facilities and better scope of doing. I said, what you do, if you leave, because he was in job, if you leave the job and go to IIC, then when you come back, you will be out of place. So better to remain in job, do your PhD, do from here and collaborate with IIC Bangalore. And it was beautiful work he has done. And he is currently, head of cancer nanotechnology at Amrita Institute of Medical Sciences in Kochi. He has got about 30 patents, 2 startups, a few PhD students and all those things. This was a wonderful work. This is first time we showed that through simple chemical method, you can make nanophosphor materials of zinc sulfide. If you see TM spectrum, it shows particle size, very uniform particle size, which is of the order of 2 to 5 or 2 to 3 nanometers. And if you see XRD pattern, it gives broad peak, which is clear indication that these are nanoparticles, but with very simple chemistry and at room temperature. This was the synthesis which was done. And yeah. slow. Yeah, this is something very interesting. You see, we tried doping. One is manganese, another is aluminium. Now, what happens when you decrease the quantity of or increase the quantity of manganese and reduce the quantity of aluminium? If you see the color change, it is coming from, say, green to orange. So what happens? Now you can tune any color between green to orange by just wearing the doping. Suppose you increase the manganese, you will go to the orange side. You decrease the manganese and increase the aluminium, you will go to green side. And what you can do, you can control put at any point. There is nothing you can have. These are 4 figures which are shown, 4 colors, but you can achieve any color. So again, it has been shown that through very, very simple method. It is again very simple chemistry, room temperature method, and very simple method. You can tune color from green to orange, and you can have any wavelength you want. Say any wavelength you want, you can have. Similarly, we could develop self-assembly, and we could show that you can have nano rod kind of thing. So this is another work on zinc sulfide. Then this is very interesting work. This is core shell. You see, core shell means what happens? You have got zinc sulfide material. When there is a vacancies, it will give blue color. As you heat it, a layer of a shell of zinc oxide is created. As you heat it, the thickness of the layer increases. So if you see here, you start with blue color, and as you increase the temperature, you get to the red color. So again here, by varying the temperature, so earlier what we did, by varying the concentration. Now what we did here, by varying the temperature. So by varying the concentration, you can tune the color. By varying the temperature, you can tune the color. And it's very interesting that there is a core of zinc sulfide and shell of zinc oxide. And as you increase the thickness of zinc oxide, this color changes and you can tune the color. So how beautifully you can tune the colors through very simple processes. This is another example, rare earth nanophosphor material. This we said multifunctional material, again core shell material. Now shell is luminescent material, core is magnetic material. So you have got magnetic material as a core and luminescent material as a core shell. So you can have a multifunctional property wherein you can have luminescence also and you can have magnetism also. And it has got a lot of applications. Now another class of material. I am trying to put across that there is a range of materials you can make very simple process. This is zinc oxide materials. This is single step process, and you can see that you can beautiful geometries of these materials, and also you have got magnetic and luminescent properties here again. Here you have you can see tuning of particle size. We call it quantum dots. So you have got say 4 nanometer, 6 nanometer, 8 nanometer particles, and you are showing that how with particle size color can be varied. So now it is third kind of tuning. Now this tuning is particle size based tuning. So now a different kind of tuning you are doing. So that's why I said it is a magnificent world of materials, because you can do many kinds of things in these materials. Okay. This is another example of silver nanoparticles. Now here again, shape and size play a very important role, and these are basically plasmonic particles. Because of plasmonic frequency, they give different colors. And you can see we could get range of colors by varying either size of the particles or by varying shape of the particles. So now here third aspect, another aspect comes that you vary the size, you get the change in color, you vary the shape, you change in the color. So now it is shape, design, color. So shape designing is there. So you can design materials in a beautiful way. This is silver nanoparticles showing luminescence, and you can see how uniformly these particles are of the order of around 3 nanometer or something like that. Again, I am emphasizing here that all these materials have been made through very simple chemical processes, most of them at room temperature, some of them at higher temperature, but very simple processes. super paramagnetic particles. So now you can vary magnetic properties. So you can see here, these are again magnetic particles, and you can see that they are kind of ferrofluids. If you see the picture, the fluid moves with the magnet. So they are ferrofluid, very stable particles, around 8 to 10 nanometer, again made in room temperature. You can make them in aqueous medium and you can make them in oily medium both. And they have lots of applications in the medical field. These are again silver nanoparticles. Then we worked on graphene and its composites. So that's again some area where we started working on it. And you can see this graphene. And this was basically for microwave absorption applications, very light, ultra lightweight material. And again, we were able to make in quantity. These are two very interesting examples which really did not involve much of synthesis, but more of observation. That is what is very important. We know barium titanate, if we know, it has got very high value of dielectric constant. It is a ferroelectric material. We were working on conducting polymers. Conducting polymers have got two forms, polyaniline. One is base and another is salt. Base is generally a kind of non-conducting and salt is conducting. And base is when non-conducting, its dielectric constant is very low. Now you see the curve here. If you take pure barium titanate, its dielectric constant is 100 plus. But if you add about 5% of polyaniline base, this dielectric constant drastically come down to around 25. Now it is not explained by any law of mixing. When you mix two materials, they should follow the law of mixing. That means they should gradually come down. But it is coming down very rapidly with very small concentration. We were struggling for about 3 months to understand how it is happening, and my PhD student used to come to me daily in the evening. Sir, ye paper, this is the paper. I used to say, nothing is available in this, nothing we are able to get. So we struggled for about 3 months. After 3 months, we could find out and we could explain the results. We also took this microscopic picture. Simple microscope, nothing like electron microscope. Microscopic picture, and what we could see is that this polyaniline base is making a very thin layer around the particles of barium titanate. Now the barium titanate gives you high value of dielectric constant because of interfacial interaction between the particles. Now what we have done, we were able to break this interfacial interaction between the particles, and since we were able to break it, so the basic process which leads to a high value of dielectric constant, that itself was removed. So once it was removed, then you got very low values of dielectric constant. Then if you see the figure here, then for all other lower values, dielectric constant is nearly about same, not varying much, but suddenly it falls down. So this we could explain through X-ray diffraction also. This we could explain through FTIR, because whenever you observe something, this is again for students very important. One study cannot provide you the concrete results. You have to corroborate with at least 1 or 2 more studies that yes, it is really like that. Then only it will be accepted in the journal, otherwise it is not going to be accepted. So though we observed the things, but to explain the things, we had to do lots of studies, and we did these studies. One more example. Yes. This is very interesting. Another example. Last example was also, I call it pistol motor research. In the sense that we had two materials, we took in a pistol motor and grinded them together and got the results. Here also it is pistol motor research in the sense that we had conducting polymer now, polyaniline, which is conducting. And we had a zinc sulfide material which is semi-conducting, but conductivity is very low. Now we know that when you make mixture of the two, what will happen? When you take zinc sulfide, low conductivity, When you take polyaniline, high conductivity, and as you change the ratio, conductivity will move from lower to higher side. But if you see two circles, closely observe these two circles, wherein you are seeing that these two composites have got electrical conductivity higher than that of polyaniline. How it can be? A composite is made, how the conductivity can be higher than highest? This was again very interesting result, and then how to explain. So we worked upon it and we got very interesting results in this. What was interesting? Interesting was that conducting polymers, they give better conductivity when they are crystalline in nature. So crystallinity is higher, conductivity is going to be higher. So that was the hypothesis which was in my mind, and let's try to understand that, and we try to work upon it. And very interesting, of course these were microscopic, very interesting X-ray diffraction studies. The lower curve is that of polyaniline. You get a peak of broad peak of polyaniline. As you increase the concentration of zinc sulfide, you see the polyaniline peak is disappearing. So zinc sulfide is working as a template for polyaniline, and polyaniline is getting better crystallinity. And because of better crystallinity, it is giving you higher conductivity. So you see, you can increase the conductivity of the material if you know real physics behind it. So this is again very interesting result we have got. So these last two examples, when I am saying, these examples were very simple research wherein we had two materials already available with us. We took in a pestle mortar, grinded them, did the studies, made the observations, explained the observations, and these two papers have got citations of 100 plus by now, and we had very good comments from the referees because they were not related to the material synthesis, they were related to the interpretation of the results. So it is very important to understand the things, make a right kind of interpretation. That is what is very important. And if we can do like that, we can do wonders. And all these wonders were done under the guidance of my mentor, Dr. N. Kumar. He was earlier director of DRDO. He was my predecessor. And these were my PhD students and also colleagues. It is basically work of them. Thank you. Jai Hind.
Now the paper is open for one or two maximum questions, short questions.
I have a simple question. Sir, when you reduce the size of a nanoparticle, so some physical parameter changes. So say melting point, whatever meter. So if we somehow arrive at the quantum dot.
Echo is there, I am not able to. You can come.
Okay, sir. So somehow if we arrive at the quantum dot configuration where everything will be theoretically zero, but is it feasible?
यहाँ आके आप वैसे ही पूछ लीजिए, फिर मैं आपका क्वेश्चन रिपीट कर दूंगा. I'll repeat your question.
If we arrive at the quantum dot configuration, then everything will be zero theoretically. Everything will be zero, everything will be zero. But is it theoretically feasible, or we have any restriction to reduce the size of the nanoparticle?
It is. There are always restrictions. Not that you can, like in case of magnetic particles, also there is a limit. Then you know what happens if you go to smaller particles. You go to single domain particles. Theoretically, there is no limit, but practically there is a limit. What method you use? Suppose you use physical method, you use chemical method. How do you start with? And then stability of the particles. How do you make them stable? Many a times what happens when you want to make them stable, you have to put coatings around that. So many things are there. Because when you are at a smaller size, reactivity is very high. When reactivity is very high, to sustain and maintain that size is also very challenging. So it's not that always you are able to get to any size you want.
Actually, I am facing a problem. I am doing the theoretical research. So I make some prediction for a relation between bulk material and nanomaterial. So that result very well in the experimental when I am talking about 5 nanometer size. But if I go beyond this, then result deviates a lot.
Yeah, he says we can discuss later on. So, yeah.
Is there any other question? If there is no other question now. Yes, please.
I don't know whether I will answer or not.
हिंदी में पूछूंगा अगर आप इजाजत दें तो हिंदी में।
हाँ, हिंदी में मैं हिंदी में बताऊंगा आराम से।
आपने अपनी जिंदगी में बहुत सारे लोगों को पीएचडी डिग्रियां दिलवाई, फिर वो आगे बढ़े। आपके बहुत सारे जो यंगर लोग थे कलीग, वो सीनियर बन गए, जैसे आपने अमृता की एग्जांपल दी।
हाँ, नहीं ये रविंद्र मंगल बैठे हैं।
या बहुत सारे ऐसे लोग हैं।
हाँ।
तो मैं आपसे सवाल ये पूछता हूँ, जब आपका बनाया हुआ कोई व्यक्ति या कैंडिडेट बहुत हाई लेवल की पोजीशन पे सडनली बैठता है, आप उसको क्या कहते हैं?
मैं एक तो कहूँगा कि ये उसका अचीवमेंट है, पहली चीज़ तो ये है, क्योंकि आपके साथ बहुत सारे लोग काम करते हैं, लेकिन अगर कोई बहुत आगे बढ़ पाता है तो कुछ तो उसमें है जिसके कारण वो आगे बढ़ा है। आपने ही थोड़ी देर पहले बोला था
एडवाइस, क्या एडवाइस?
हाँ, एडवाइस में मैं ये बता देता हूँ, आपने भी थोड़ी देर पहले बोला था, मैं उसको प्रैक्टिस करता हूँ, आप भी प्रैक्टिस करते हैं। एडवाइस ये है कि अगर मान लो मैं कहता हूँ नेक्स्ट जनरेशन ठीक नहीं है, तो कहीं ना कहीं मैं गलत हूँ। पहली चीज़ तो ये मानता हूँ कि अगर नेक्स्ट जनरेशन को मैं ब्लेम करता हूँ तो कहीं ना कहीं मैं गलत हूँ, क्योंकि मैं ही उसका मेंटर रहा हूँ। मैं मतलब आवर कम्युनिटी, आवर पीपल। एक तो ये चीज़ है। दूसरा जो बहुत इंपॉर्टेंट चीज़ ये है कि अलाउ पीपल टू ग्रो, बिकॉज दे विल बी रिसोर्स फॉर द कंट्री एंड दे विल बी रियल रिसोर्स फॉर द कंट्री। जिसमें अच्छा, लेकिन एक और भी चीज़ है, जिसमें काबिलियत होगी, आप उसको रोक तो पाओगे नहीं, उसको आप धीरे करोगे। तो आप धीरे क्यों करना चाहते हो? एक। दूसरा, मैंने एक और चीज़ मैं खुद मानता हूँ और मैं सोचता हूँ कि जब आप अपने से नीचे वाले लोगों को ऊपर आने देते हैं तो आपका कद अपने आप बढ़ जाता है, योर लेवल ऑटोमेटिकली गोज अप। तो आप क्या कर रहे हैं? उसको रोक के अपने आप को भी रोक रहे हैं। तो मतलब सबसे पहले तो आप अपने आप को रोक रहे हैं दूसरे को रोक के। सो नेवर डू दोज थिंग्स, यू अलाउ पीपल टू ग्रो, बिकॉज वो बहुत ज़रूरी है। और अगर आप नहीं करते हो तो सबसे गलत, सबसे ज़्यादा नाइंसाफ़ी आप अपने खुद के साथ कर रहे हो। और कोई भी क्यों बेवकूफ़ी करेगा जो अपने साथ नाइंसाफ़ी करेगा? कम से कम मैं तो ऐसा बेवकूफ़ इंसान बनना नहीं चाहता। ये और मैं शेयर करना चाहूँगा। पहले तो मतलब मैं तो कुछ लोगों के साथ, मतलब आई फील वेरी प्राउड टू बी एसोसिएटेड विद पीपल। रविंद्र मंगल एक है जो कि फिजिक्स को इतना कंट्रीब्यूट कर रहे हैं, और मैं जब भी इनको देखता हूँ तो मुझे एक नई ऊर्जा मिलती है। आई गेट ए न्यू एनर्जी। एक तो ये चीज़ है। दूसरा मैं बता रहा हूँ, जिसकी मैं बात कर रहा था, जो बंदा प्रोफेसर है, हाँ, द पर्सन हु इज प्रोफेसर, yeah, absolutely, I can always, since he wanted, I did it, but I can always. So what happened, this person who is right now professor, who got professor at the age of perhaps 36 or 38, very young age and all these things, that's okay. When he met me for the, after a few days of joining with me in DRDO, maybe 2 months, 4 months or something, then he came to me and he said, "Sir, I want to tell you something." I said, "Tell me." "Sir, I want to become like you." And I banged him like anything. I said, "Nonsense, what are you talking?" and all this. "Sir, did I tell anything wrong?" I said, "Yes." "Sir, what did it?" I said, "You told wrong. You have kept your target very low. The day you become better than me, I'll be truly happy about it. And this is what has to be in a teacher, and this is what is a true teacher. When you see your students growing higher than you, that is your achievement. And that is your contribution. And that is what we should all aspire for. That's what I have practiced. And I wish if we can all do, we can make this world wonderful. World wonderful, not India. Thank you.
Thank you, sir. Thank you for your wonderful session, and thanks to the chairman and the co-chairman of the session, who has handled this session very beautifully. And we have seen some expert lectures, the keynote lectures. Now, I'll request Professor Sampath Kumar Vishwas to kindly hand over the memento to Professor J.V. Yakmi for the keynote lecture that he has delivered. May I request Yakmi, sir? Sir. May I request Professor Narendra Bhojak, sir, to kindly hand over the memento to Dr. Michael D. Loro. And may I request again to Professor Narendra Bhojak, sir, to hand over memento to Professor Sampath Raj Vadera, sir. May I request Dr. Manoj Shekhawat, sir, to hand over memento for acting as chairman to the session to Professor Sampath Kumar Vishwas. I also request again to Manoj Shekhawat, sir, to hand over the memento to Professor Narendra Bhojak, sir, for acting as co-chairman of the session. Thank you all. Now we have this little break for the high tea, and we will assemble here again after 10 minutes. After 10 minutes, again we will assemble here for the next session. So thanks to all, and we will meet after this tea break. Thank you.